Welcome to Brain Vision.
Okay, so we have an equilateral triangle, so each side is length A, and we have a current I flowing through it, going counterclockwise. And so then a distance d below the triangle, we have an infinitely long wire carrying a current I prime. And as usual, then we want to find what the force acting on the triangle is due to the magnetic field produced by the long wire here. So what we usually want to do then is look at the force that acts on each side of the triangle or any kind of loop that we're dealing with, since that'll usually simplify things a lot. So I'll call this bottom side, side 1, and then side 2, and side 3. So most generally then, the net force on the triangle is just the force produced by side 1 plus the force produced by side 2 plus the force produced by side 3. So side 1 we can deal with pretty easily. So this is parallel to the wire down here, and the current's flowing in the same direction. So that tells us it's going to be an attractive force. So if it's being attracted, it's going to be pulled in the downward direction. So we usually call that negative. So we can say then that this force is just going to be negative, and then the magnetic field produced by this wire is mu naught I prime over 2 pi times the distance, so that's d, and then just times the current here, and then the length that it's carrying over. So just times I, and then times a. So this is all F1. And now looking at F2 and F3. So sometimes we're lucky and these two forces will just cancel out in these kind of loop problems, but doesn't look like that's going to happen here. So we can see that the vertical current between the two is going to cancel. So because there's so much symmetry here, any kind of upward current traveling in wire 2 is canceled out by downward current traveling in wire 3. So the forces they produce are going to cancel. But we can see there's a net horizontal current. So there's current going in the negative x direction for wire 2, and there's also current going in the negative x direction from wire 3. And so that means then there's going to be a repulsive force since the overall current is going the opposite direction here. So also by symmetry, though, we can see that those two forces are going to be equal to each other. So to kind of simplify this a little bit then, this will now be a positive force, and so this is plus, and really they're the same magnitude, so we can just say plus 2 times, we'll find the one on F3, as I think that one will be a little easier just coordinate system-wise. So times 2 F3. And so, yeah, and so I've kind of been a little sloppy with the signs here, so this is sort of the more standardized equation we're working with now. So now we just need to find F3 or F2, any of the forces that are acting on these two things. So to do that, we have to use our normal force equation for current going through wire, but we're going to have to integrate it. And that's because if we look at the distance between the long wire down here and the portion 3 of this wire, you can see that that total distance is changing along the length of it. So because this is an equilateral triangle, we know halfway through here is just a distance A2. So we want to start at this point here, which I'll call position 0, and go to the right. So that's why we're looking at wire 3. That just seemed a little easier than going in the negative direction. So we want to start here and integrate across a distance A over 2. And integrates the total force that's acting on this wire here. So we'll just look at F3 then. And so that's going to be an integral. We're going from 0 to A over 2, so across the full horizontal length of the wire, but not necessarily the whole length of the wire itself. And so we have the magnetic field, which is mu naught I prime over 2 pi r in general. There we'll have to deal with that. And then times the current in portion 3, and then we'll integrate this with respect to x, so we're integrating along this direction. So we're going to need to figure out, well, what is r here? So the distance that we're away from a point on here, if we look at different points is clearly going to depend on our horizontal position along here. So the farther we move along this part of the triangle, the higher up it gets here. And so the farther from the wire down here it is. So let's kind of zoom in a little bit on a part of this triangle. So here's still wire 3. And let's say we're looking now at this part, a little dx part way up there. So its total distance from the wire down here is going to be d, but then the minimum distance is then also going to have this little vertical part here. So this distance and then plus d is the shortest distance down to the wire here. So what will this height here be? Well, this is an equilateral triangle, so we know this angle is 60 degrees. So we can say then this distance will be x, so this point will be a distance x away from where we're starting. That's why we're integrating with respect to x. And so this height here then, this h, would just be, could do tangent of 60, so opposite over adjacent, and then tangent of 60 is root 3. So we'll find this h is root 3 times x. So that means then r, our total distance from the wire up to this point here, is just d plus x. And so that will be d plus h. So that will be then d plus root 3x. So now we substitute that in for r over here. And I'm going to go ahead and pull out a bunch of these constants. So we'd have mu naught I prime I over 2 pi. And so now we're just integrating from 0 to a over 2 dx over r, which is d plus root 3x. So I think I'll go on to a new page for this. But that is a classic log integral, so you can look this up in a table or you could do a use substitution. But you should find then that that becomes, with our big constants out here still, mu naught I prime I over 2 pi. This should evaluate to just natural log of d plus root 3 times x. And we were evaluating that from 0 to a over 2, so across half of the triangle. So we plug in those limits, and I think I'll just call this big constant c. Then we have c times natural log, and this will end up being 1 plus root 3a over 2d. So I'm using the fact there that if you have ln of a minus ln of b, you can just write that as ln of a over b. Okay, so there is our force made from section 3, and that's in the negative x direction. And then by symmetry, we know section 2 makes the exact same force. And we've already found our force from section 1. So now we can add all of these up. And so our net force then is the force from section 1, so mu naught I prime times a over 2 pi d. And that was an attractive force. Oh, so I'm sorry, so this is in the force from a is in the negative direction, the negative y direction, and the force from 2 and 3 are in the positive y direction. Like I said, x before. And then we have now, so that is negative, and our other two forces are positive because they're being pushed vertically, being pushed up. And so it'll just be twice this force since we have section 2 and section 3. So 2 times c, and then ln of 1 plus root 3a over 2d. And this constant c looks like is pretty close to something we have here. And so if you fiddle with that a little bit and factor things, you can get this, should be able to get this down to mu naught I prime a, or sorry, just I prime times pi. And then this whole thing times a over 2d minus root 3 over 3 natural log of 1 plus root 3a over 2d. So this whole thing is probably about the simplest looking you can get it. Personally, I don't think there's really anything wrong with this answer up here. I don't think there's a whole lot of insight to be gained from writing it like this, but it does look a little prettier. So one of these two versions, or kind of however you've managed to simplify it in the end. And so this whole thing then, as we've written it, is in the y hat direction.